In this lecture, we're going to talk about interest rate conversions. In particular, we're going to cover two topics. We're first going to talk about timescale conversions, and then we're going to talk about the conversion of nominal interest rates versus effective interest rates. Let's talk about timescale conversions first. Up to this point in the course, whenever we've given you a problem, and there's been a period of time over which the cash flows occurred, the interest rate that we gave you for that problem matched that period of time. Now, most of the problems we've dealt with have been the increment of time 1 year. So if we gave cash flows that occurred on an annual basis, we gave you an interest rate that was also on an annual basis. In practice, there will be times when, in fact, the period of time at which the cash flows occur is different than the interest rate you may be given. Cash flows may be occurring, say, every 6 months, but the interest rate you have is, say, an annual interest rate. Like any engineering problem, we have to be certain that the dimensions of all the elements in that problem match. If the cash flows are occurring on a 6-month basis, then the interest rate we use in our equivalence calculations also has to be on a 6-month basis. If the cash flows are annual, the interest rate needs to be annual. Timescale conversions refer to that situation where we need to be able to convert an interest rate from one time scale to another one. Let's take an example. Let's take this situation. If you were offered a quarterly interest rate, and we'll give that the symbol I sub 4, of 4% per quarter year, what semi-annual interest rate, that is every 6 months, let's give that the symbol I sub 2, would make you indifferent between having 4% per quarter year or the semi-annual rate I sub 2, meaning by indifferent, if offered one or the other, you wouldn't care because financially they're equivalent. Basically, to solve this problem, we need to solve an equivalence problem. In particular, let's represent it this way. Let's show our cash flow diagram this way over a 1-year period of time in which we've divided the year up into 4 quarters as well as 2 half-year increments. If we wanted to identify a semi-annual interest rate that is equivalent to a given quarterly interest rate, what we need to be able to show is if I was given some present sum P, and I were to invest those funds each quarter for 4 quarters at 4% per quarter year, it would produce some future amount. What I need to demonstrate is if given that same present sum and invested at the semi-annual rate for 2 periods, it would result in the same future amount. If I can show that, then those interest rates are equivalent. I can write the equation this way. This future sum F is equal to a given present sum times 1 plus the quarterly interest rate compounded 4 times. But I also want that to be equal to that same present sum when compounded forward at the semi-annual interest rate I sub 2 compounded twice. All I do now is simplify and rearrange this formula, and I produce this equation. That is, the semi-annual interest rate that's equivalent to a quarterly interest rate is 1 plus the quarterly interest rate raised to the power 4 divided by 2 minus 1. All I have to do now is substitute in my known quantities, which are 4% per quarter year, compounded twice, that is 4 divided by 2 minus 1, results in a semi-annual interest rate of 0.0816. Notice, the semi-annual interest rate that's equivalent to a quarterly interest rate of 4% per quarter is slightly more than 8% per year. That is, it's not exactly 8%. It's not twice the quarterly rate. Why? Compound interest. You're getting interest on interest. So the semi-annual interest rate that's equivalent to 4% per quarter year is 8.16% per year. If I offered you 4% per quarter year or 8.16% semi-annually, you'd be indifferent. Those are equivalent interest rates. Now, we need to be able to do this on any time scale, not just quarterly to semi-annually, and so we can generalize that this way. Here again, I've shown my cash flow diagram where I've divided the year up into two time scales. One is M2 periods per year, and the other is M1 periods per year. In my preceding problem, M2 was 4 and M1 was 2. Again, if I wanted to be able to convert an interest rate from a time scale of M2 periods per year to, say, M1 periods per year, I need to be able to demonstrate that if I took a present sum P and I compounded it forward M2 times to accumulate a future sum F, that I would get the same future sum if I were to take that present amount P and compound it forward M1 times. I write the formula this way: F is equal to the present sum times 1 plus the interest rate when funds are compounded M1 periods per year, has to be equal to the present amount when those funds are compounded forward M2 periods per year. Simplifying and rearranging the formula, you end up with this very general equation. The interest rate when funds are accumulating at M1 periods per year is equal to 1 plus the interest rate when funds are accumulating at M2 periods per year, raised to the power M2 divided by M1 minus 1. Let's talk about nominal versus effective interest rates. And in particular, let's talk for a moment about a nominal annual interest rate. Nominal interest rates are fairly common in the financial community, and they're largely the result of historical convention, and we need to be aware of them. Nominal interest rates are typically represented this way. We'll use the symbol lowercase r represents the nominal annual interest rate. M represents the number of compounding periods per year, and I sub m represents the effective interest rate for the compounding periods of M per year. Let's take an example. Credit cards often charge 1.5% per month for the unpaid balance and report it typically on their statements as 18% compounded monthly. And the manner in which they calculate that 18% is this. They take 12 months times the monthly interest rate of 1.5%, and that results in 18%. Now, hopefully, you'll notice that this nominal annual interest rate does not take into account compound interest. Simply taking the number of months and multiplying by the monthly interest rate doesn't account for compound interest. In engineering economy studies, we want to work with effective interest rates, that is, interest rates that recognize compounding of interest over time. The point here is, if you encounter a nominal annual interest rate in the process of doing an engineering economy study, what you need to do is to be able to convert that nominal annual interest rate to its effective interest rate and to work with the effective interest rate in doing your calculations. Basically, you'll need to be able to undo what they have done to calculate that nominal rate. The rate you want is I sub m. Once I have I sub m, I can convert that to any other time scale using the concepts that we just talked about at the beginning of this lecture. For example, if I were to ask the question, if you had this credit card and you were to make some purchases and to leave those purchases unpaid month to month for the next 12 months, this credit card would charge you 1.5% every month that those balances remain unpaid, and they would charge you interest on interest every month. So the effective annual interest rate that you would pay would look like this. You would pay 1.5% per month over 12 months would accumulate to roughly 19.6%. In other words, almost 20% per year is what you're paying for the use of those borrowed funds. Let's take another view of the word effective interest. Let's assume we have the following scenario. A bank offers loans of $2,500 for 30 months at an advertised interest rate of 2% per month. The monthly payments are computed as follows. The interest is calculated as 2% per month times the amount borrowed times 30 months results in a total amount of interest owed of $1,500. They're also going to charge you a processing fee to take out this loan of $50. So the total amount owed will be the original amount borrowed, $2,500, plus the total interest of $1,500, plus that processing fee, for a total of $4,050. They then take the total owed and they divide by the number of months, 30, and they end up with payments of $135. What is the effective annual interest rate on this loan? Now, it's not particularly material how it is they went through these calculations. What we need to be able to do is to convert this problem statement to a representation of the net cash flow series involved with taking out this loan. If we do that, that cash flow series looks like this. Basically, the loan that's being offered is this. You can borrow $2,500 today, and for the privilege of doing that, you will owe the bank $135 each month for the next 30 months. That's the loan that's being offered to you. Now, how the bank got to the calculation here, that final amount of $135, really is not material. What's material to you is that is the final outcome. This is what you're going to have to pay. There is an implied interest rate in this loan. All we have to do is to find a present amount of these payments that's equivalent to $2,500 and solve for the unknown interest rate, and that will be the interest rate on the loan. In other words, we'd write the equation this way. We'll take $2,500 as the amount borrowed, and we want to find an interest rate, in this case a monthly interest rate, such that when we discount this uniform stream of $135 back to time zero over a 30-month period, it results in $2,500. Now, this is a trial and error sort of a calculation, and if you do that, you'll find that that monthly interest rate for this loan works out to be about 3.6% per month. If I wanted to know what is the effective annual interest rate that I'm paying, then I go through a time scale conversion. I will convert this monthly rate to an annual rate, and I will do that by using my formula. 1 plus the monthly interest rate compounded 12 times minus 1 results in an effective annual interest rate of almost 53% per year. That is a pretty expensive loan. Let's summarize the concepts we've talked about in this lecture. We first talked about timescale conversions. That is, there will be situations when we will have interest rates in one time scale, and we would like to be able to convert those interest rates to another time scale. To do that, we derived this very general formula. We then talked about nominal versus effective interest rates, and we commented that nominal interest rates occur mostly in the financial community, and they're largely a result of historical convention. In engineering economy studies, we want to use the effective interest rates. The manner in which one calculates a nominal interest rate was shown by this equation. We demonstrated that to calculate the equivalent effective annual interest rate given that nominal interest rate was demonstrated through that equation. And then finally, we went through an example at the end where we demonstrated the notion of effective interest rate means it includes all costs, processing fees and everything. Timescale conversions and nominal versus effective interest rates are things that we will encounter from time to time in the balance of the course. And we need to be able to make these calculations and to convert them to be able to do a proper engineering economy study.